You are staring at a clock. The pendulum swings left, then right, left, right. It has done this for hours, for days, and every swing costs something. Friction, heat, energy bleeding away into the universe. Eventually, it will stop. Everything stops. The coffee cools, the spinning top falls, the stars themselves will burn out. This is the second law of thermodynamics, one of the most ironclad rules in physics. Entropy always increases, motion always decays. Nothing moves forever, or so we thought. For centuries, physicists believed this was an absolute law, as unbreakable as the conservation of energy itself. Inventors and dreamers proposed perpetual motion machines, devices that would run forever without any input of fuel or power. And every time, physicists showed that these machines could not work. They violated either the first law of thermodynamics, which says you cannot create energy from nothing, or the second law, which says you cannot perfectly convert heat into work without some waste. The dream of perpetual motion seemed dead. Physics had spoken, and physics said no, except in 2017, scientists at Harvard and the University of Maryland announced that they had created something that should not exist. A new form of matter whose atoms move in a repeating pattern, oscillating back and forth in time forever without losing any energy. A form of matter that, in some deeply unsettling way, breaks time itself. They called it a time crystal, and what it reveals about the nature of reality is far stranger than the name suggests. To understand why time crystals are so extraordinary, we need to understand what makes an ordinary crystal extraordinary in the first place. And then we need to understand something even deeper: what symmetry means in physics, and why breaking it is the key to nearly everything in the universe. Pick up a grain of salt, hold it between your fingers. To your eyes, it looks like a tiny cube. But if you could shrink yourself down to the size of an atom and walk through it, you would find yourself in a world of perfect geometric order. Sodium atoms and chlorine atoms arranged in a three-dimensional grid, repeating the same pattern over and over in every direction: up, down, left, right, forward, back. The same arrangement, the same distances, the same angles. On and on, billions of atoms, all locked into the same crystalline structure. This is what physicists mean when they talk about spatial periodicity. The crystal repeats in space. It has a pattern, and that pattern extends throughout the material. This repetition is not trivial. When atoms arrange themselves into a crystal, they are choosing a specific structure out of infinitely many possibilities. Before the crystal forms, when the atoms are in a disordered liquid state, every position in space is equivalent. The laws of physics look the same at every point. But once the crystal solidifies, this equivalence is broken. Some positions now contain atoms, others do not. The crystal has selected a particular lattice, one possibility out of infinitely many. Physicists call this spontaneous symmetry breaking. The symmetry of the underlying laws, which treat all positions equally, is broken by the actual state of the system, which treats lattice sites as special. The crystal remembers a choice that was not determined by the fundamental equations, but emerged from the physics of the transition. This concept, spontaneous symmetry breaking, is one of the most powerful ideas in modern physics. It explains why magnets have north and south poles, even though the laws governing magnetism do not prefer any direction. It explains why superconductors can carry current without resistance, even though ordinary metals cannot. And through the Higgs mechanism, it explains why elementary particles have mass at all. Symmetry and its breaking are central to our understanding of the physical world. And in 2012, Frank Wilczek asked whether one of the most fundamental symmetries of all could be broken in a new way. Now here is the question that would change physics. In 2012, a theoretical physicist named Frank Wilczek was preparing to teach a class at MIT about symmetries in physics. Wilczek was not just any physicist. In 2004, he had won the Nobel Prize for his work on the strong nuclear force, the force that holds atomic nuclei together. He was one of the most creative minds in theoretical physics. And as he sat thinking about crystals, he had an idea that seemed almost absurd. If atoms can arrange themselves into a repeating pattern in space, could they also arrange themselves into a repeating pattern in time? The question sounds simple. The implications are anything but. To understand what Wilczek was really asking, we need to understand symmetry. Not the everyday kind of symmetry you might think of, like the symmetry of a butterfly's wings. Physicists mean something more fundamental. In physics, a symmetry is a transformation you can perform on a system that leaves the laws governing it unchanged. If you pick up your salt crystal and move it 3 feet to the left, the laws of physics that govern its atoms are exactly the same. This is called translational symmetry in space. The location in space does not matter. The laws are the same everywhere. There is another symmetry just as fundamental: translational symmetry in time. If you performed an experiment yesterday and you perform the exact same experiment tomorrow, the laws of physics will give you the same results. The time does not matter. Physics works the same way at all times. In 1915, a brilliant mathematician named Emmy Noether proved something remarkable. Every continuous symmetry in physics corresponds to a conservation law. Translational symmetry in space corresponds to the conservation of momentum. Rotational symmetry corresponds to the conservation of angular momentum. And translational symmetry in time corresponds to what might be the most famous conservation law of all: the conservation of energy. Noether was working in Göttingen, one of the world's greatest centers for mathematics at the time. She had been invited there by David Hilbert and Felix Klein, two giants of mathematics, to help them understand some puzzling features of Einstein's new theory of general relativity. In the process, she proved a theorem that would become one of the cornerstones of theoretical physics. Before Noether, the conservation laws seemed like arbitrary rules. Energy is conserved, momentum is conserved, angular momentum is conserved. Why? No one could say. There were simply observations, empirical facts about the world that physicists accepted without deep explanation. Noether showed that these laws were not arbitrary at all. They followed inevitably from the symmetries of the fundamental equations. The reason energy is conserved is that the laws of physics do not change with time. The reason momentum is conserved is that the laws of physics do not change from place to place. The reason angular momentum is conserved is that the laws of physics do not care which direction you call north. Albert Einstein called Noether's work a piece of penetrating mathematical thinking. Today, her theorem is taught in every advanced physics course and applied in every theoretical physics calculation. Think about that. The reason energy is conserved, the reason you cannot create energy from nothing or destroy it into nothing, is because the laws of physics do not change with time. Time translation symmetry is the mother of conservation of energy. This connection has profound consequences. It is the reason perpetual motion machines are impossible. If you could build a machine that ran forever without any input of energy, you would be violating conservation of energy, and that would mean breaking time translation symmetry itself. It would mean the laws of physics are different at different times, which they are not. At least, that is what physicists believed for over a century. When Wilczek imagined a time crystal, he was imagining something that seemed to violate this fundamental principle. He pictured a quantum system, a ring of particles perhaps, that would spontaneously start moving in a repeating pattern in time. The particles would oscillate. They would change states, then return to their original state, then change again over and over in a periodic rhythm. And crucially, they would do this in their ground state, their state of lowest possible energy, without any external input. If this sounds like a perpetual motion machine, you are not wrong to think so. Wilczek was proposing a system that would move forever, without any energy being added or removed, at the minimum possible energy. A clock that never needs winding. A pendulum that never stops swinging. Wilczek published his proposal in February 2012 in a paper titled Quantum Time Crystals. The physics community reacted with a mixture of fascination and skepticism. The fascination was obvious. A new form of matter, one that breaks time symmetry the way ordinary crystals break space symmetry, would be a discovery of enormous significance. It would open up entirely new areas of physics. But the skepticism was equally justified. Within a year, physicists began publishing papers arguing that time crystals were impossible. Patrick Bruno of the European Synchrotron Radiation Facility in France was one of the first to raise objections. Then, in 2015, Haruki Watanabe of the University of California, Berkeley, and Masaki Oshikawa of the University of Tokyo published what seemed to be a definitive proof. Time crystals, as Wilczek had imagined them, could not exist. Their argument was elegant and devastating. Any system in thermal equilibrium, any system that has settled into its lowest energy state, cannot spontaneously break time translation symmetry. The mathematics was clear. Time crystals, like so many beautiful ideas before them, appeared to be a dream that physics would not allow. Frank Wilczek's vision, it seemed, had been killed by a theorem. But physics has a way of finding loopholes, and the loophole for time crystals would come from an unexpected direction: the study of disorder. In 1958, a physicist named Philip Anderson, working at Bell Labs, discovered something strange about electrons in disordered materials. Normally, electrons in a metal can flow freely through the material. That is what makes metals good conductors of electricity. But Anderson showed that if you introduce enough randomness into the material, enough disorder in the arrangement of atoms, the electrons can become trapped. They localize. They cannot move through the material at all. The physics is subtle but beautiful. An electron in quantum mechanics is not a point particle. It is a wave. As the wave moves through a material, it scatters off impurities and defects. In a perfectly ordered crystal, these scatterings combine coherently, allowing the wave to propagate through the material. But in a disordered material, the scatterings interfere destructively. The wave function breaks apart, cancelling out everywhere except in a small region. The electron becomes localized, trapped by the very randomness that should have scattered it away. Anderson called this phenomenon the absence of diffusion in certain random lattices. Today, we call it Anderson localization, and it earned him the Nobel Prize in Physics in 1977. But for decades, it remained largely a curiosity, a specialized topic in condensed matter physics. The systems that displayed Anderson localization were esoteric: electrons at very low temperatures, photons in carefully engineered optical media, ultra-cold atoms in disordered potentials. Then, in the 2000s, physicists began asking a new question. Anderson localization applies to single electrons moving through a disordered landscape. But what happens when you have many particles that are interacting with each other? What happens when the electrons can push and pull on one another? The answer turned out to be something called many-body localization. In a many-body localized system, even the interactions between particles cannot break the localization. The particles remain stuck. The system cannot thermalize. It cannot reach equilibrium. It cannot explore all the possible states that statistical mechanics says it should explore. This is profoundly weird. In ordinary physics, isolated systems always eventually reach thermal equilibrium. If you put a hot object next to a cold object, heat flows until they are the same temperature. Energy spreads out. Entropy increases. The system relaxes into its most probable state. But a many-body localized system does not do this. It remembers its initial conditions. It stays out of equilibrium indefinitely. The second law of thermodynamics still holds, technically, because entropy is not decreasing. But the system is not thermalizing either. It is frozen in a strange limbo, neither hot nor cold, neither ordered nor disordered. And this, it turned out, was exactly the loophole that time crystals needed. In 2016, a graduate student at Princeton named Vedika Kamani was studying many-body localization with her advisor, Shivaji Sondhi. They were exploring what happens when you periodically drive such a system, when you kick it with a regular pulse of energy. Normally, if you drive a system with a periodic force, one of two things happens. Either the system absorbs energy from the drive and heats up until it reaches infinite temperature, or the system synchronizes with the drive and oscillates at the same frequency. But Kamani and Sondhi found something different. In a many-body localized system, neither of these things happens. The localization prevents the system from absorbing energy. It cannot heat up. And because it cannot thermalize, it can respond to the drive in an unexpected way. It can oscillate at a frequency different from the drive. Specifically, they found that the system could oscillate at half the drive frequency. If you hit the system twice per second, it would oscillate once per second. If you hit it at 100 Hz, it would respond at 50 Hz. The system was breaking the time translation symmetry of the drive. This was not quite Wilczek's original vision. He had imagined a time crystal in equilibrium, in its ground state, moving without any external drive. That, as the no-go theorem showed, is impossible. But this was something different. This was a discrete time crystal, a periodically driven system that breaks the discrete time symmetry of the drive. At almost the same moment, another group was reaching the same conclusion from a different direction. Dominic Elsa, Bauer, and Chetan Nayak at Microsoft's Station Q and UC Santa Barbara independently proposed the concept of Floquet time crystals, named after the 19th century mathematician who developed the mathematics of periodically driven systems. The race was on to actually build one. The years between 2016 and 2017 were feverish in time crystal research. Multiple groups raced to be the first to experimentally demonstrate this new phase of matter. The theoretical frameworks were in place. Kemeny and Sondi at Princeton, Elsa and Nayak at Microsoft Station Q, Yao and Vishwanath at Berkeley. But theory is not experiment. Mathematical proofs do not make matter. Someone had to actually build a time crystal and show that it worked. The challenge was significant. To create a discrete time crystal, you needed three things. First, you needed a system of interacting quantum particles, spins or atoms or electrons that could influence each other. Second, you needed disorder, randomness in the system that would prevent it from thermalizing. Third, you needed a periodic drive, a repeating pulse that would establish the time translation symmetry to be broken. Each of these requirements pushed the limits of experimental technique. Creating precisely controlled interacting quantum systems was the province of specialized laboratories with millions of dollars in equipment. Introducing the right kind of disorder, enough to localize the system, but not so much as to destroy its coherent behavior, required careful calibration, and the periodic drive had to be applied with exquisite precision, the timing controlled to nanoseconds or better. In late 2016, Norman Yao, a physicist at UC Berkeley, published a blueprint. His paper, appearing in Physical Review Letters, laid out exactly what a discrete time crystal should look like, how to build one, and how to verify that you had succeeded. The key ingredients were clear. You needed a system of interacting particles. You needed disorder to prevent thermalization. And you needed a periodic drive. The drive would flip the spins of the particles like flipping tiny bar magnets upside down. And if the system was truly a time crystal, the spins would oscillate at half the frequency of the drive, even if the drive was imperfect. That last part was crucial. In an ordinary system, if you flip the spins imperfectly, if your drive is slightly off, the system will eventually synchronize with the drive or fall apart into chaos. But in a time crystal, the subharmonic response is rigid. It is protected by the many-body localization. It is a true phase of matter, not just a transient behavior. Two experimental groups immediately set out to build Yao's time crystal. One, led by Christopher Monroe at the University of Maryland, used a chain of 10 ytterbium ions trapped in an electromagnetic field. The other, led by Mikhail Lukin at Harvard, used nitrogen vacancy defects in diamond, tiny impurities where nitrogen atoms replace carbon atoms in the diamond lattice. Both approaches were technically brilliant. Both pushed the boundaries of experimental physics. And in March 2017, both groups published their results in the same issue of Nature. They had done it. They had created time crystals. In Monroe's experiment, 10 ytterbium ions floated in a vacuum chamber, suspended by oscillating electric fields that created a kind of electromagnetic cage. Each ion behaved like a tiny quantum spin, pointing up or down. Laser beams flipped the spins and made them interact with each other. Additional laser beams created disorder by giving each ion slightly different properties. The experimenters hit the ions with a sequence of laser pulses. First, a pulse to flip all the spins, then pulses to create random spin-spin interactions. Over and over, a periodic drive, and they watched what happened. The spins oscillated, up, down, up, down. But here was the key observation. Even when the experimenters deliberately made the spin flip pulses imperfect, even when the drive was not exactly synchronized, the spins still oscillated at exactly half the drive frequency. The oscillation was locked. It was rigid. It did not drift or decay. The system still locked at a very stable frequency. Monroe explained in interviews, "Spatial crystals are resistant to any attempt to nudge their atoms from their set spacing. This time, crystal has the same thing, only in time instead of space." At Harvard, Lukin's experiment was completely different in its physical implementation, but showed the same essential physics. The nitrogen vacancy centers in the diamond created nearly 1 million quantum spins, each one a tiny magnetic moment. Microwave pulses flipped the spins. The natural disorder in the diamond, the random spacing of the defects, provided the localization. And the result was identical. Period doubling. Subharmonic response. A true time crystal. Phil Richarm of Indiana University, who was not involved in either experiment, summarized the significance in a perspective piece accompanying the papers. Observation of the discrete time crystal confirms that symmetry breaking can occur in essentially all natural realms and clears the way to several new avenues of research. Such similar results achieved in two wildly disparate systems underscore that time crystals are a broad new phase of matter, not simply a curiosity relegated to small or narrowly specific systems. The 2017 experiments were proof of concept. They showed that time crystals could exist, but they left many questions unanswered. How stable were these crystals, really? Could they survive for longer than a few hundred oscillation cycles? Were they truly in the many-body localized phase, or were they just very slowly thermalizing? To answer these questions would require a new kind of experiment. And in 2021, it came. On November 30th, 2021, a team of scientists from Stanford, Google Quantum AI, the Max Planck Institute for Physics of Complex Systems, and Oxford University published a paper in Nature that represented a new kind of milestone. They had not just created a time crystal. They had created one inside a quantum computer. Google's Sycamore processor, the same chip that had claimed quantum supremacy in 2019, became the platform for a time crystal experiment. The researchers used 20 qubits, the quantum bits of information at the heart of quantum computing. They programmed these qubits to behave like interacting spins, complete with disorder and periodic driving. The advantage of using a quantum computer was control. Unlike atoms in a trap or defects in a diamond, qubits can be programmed precisely. Their interactions can be tuned. The drive can be adjusted. And most importantly, the quantum computer can run the simulation backward. That last capability was crucial. One of the challenges in time crystal research is verifying that the crystal is truly stable. In any real experiment, there are imperfections, noise, errors. The time crystal oscillates for a while, but eventually the oscillations decay. Is this decay fundamental, or is it just because the experiment is imperfect? By running the simulation backward, the researchers could effectively undo the imperfections of the quantum computer and see what the ideal time crystal would look like. They could distinguish between fundamental decay and experimental noise. We managed to use the versatility of the quantum computer to help us analyze its own limitations, said Roderick Mersner, co-author of the paper and director at the Max Planck Institute. It essentially told us how to correct for its own errors so that the fingerprint of ideal time crystalline behavior could be ascertained from finite time observations. The result was clear. The time crystal was stable, not for a few hundred cycles, but indefinitely. In the ideal limit, without experimental imperfections, the oscillations would never decay. The time crystal would tick forever. If the implications are not yet clear, let me spell them out. A time crystal is matter that moves without consuming energy. Its atoms oscillate back and forth endlessly, and this motion is not borrowed from anywhere. It is not extracted from a battery or a fuel source. It is intrinsic to the state of the matter itself. This sounds like it should violate the laws of thermodynamics. It sounds like perpetual motion, but it does not, for reasons that are subtle and important. First, a time crystal is not doing work. It is moving, yes, but it is not pushing against anything, not lifting weights, not driving machines. The oscillation is pure motion without purpose, dance without labor. You cannot extract energy from a time crystal without putting energy in first. Second, a time crystal is not in equilibrium. The no-go theorem of Watanabe and Oshikawa proved that equilibrium systems cannot form time crystals. But a periodically driven system is not in equilibrium. It is being kicked over and over by an external drive. The trick is that a many-body localized system can be kicked without absorbing the energy of the kicks. The drive provides the rhythm, but not the power. Think of it this way. When you push a child on a swing, your pushes add energy to the swing. The child goes higher and higher with each push. But a time crystal is different. The drive establishes a rhythm, but the system does not absorb the drive's energy. Instead, the many-body localization prevents energy absorption. The system responds to the drive without being heated by it. This is deeply counterintuitive. In almost every other physical system, periodic driving leads to heating. If you put a cup of water in a microwave, the electromagnetic waves heat the water. If you shake a box of sand, friction heats the sand. Energy flows from the drive into the system, increasing the system's temperature and entropy. But many-body localization breaks this pattern. The localization prevents the system from reaching thermal equilibrium. And if the system cannot equilibrate, it cannot heat up. The drive kicks the system, but the kicks bounce off without being absorbed. Third, entropy is not decreasing. The second law of thermodynamics says that entropy can never decrease in an isolated system. A time crystal is not an isolated system. It is coupled to the drive. And within the many-body localized phase, entropy stays constant. It does not increase because the system cannot thermalize. It does not decrease because the oscillation does not create order from disorder. The time crystal sits precisely on the edge of the second law, satisfying it marginally, technically legal, but deeply weird. As Vedika Kamani put it in a 2023 interview with Quanta magazine, the laws of thermodynamics simply do not apply in the settings that I was telling you about. We are talking about quantum systems that can remain out of equilibrium, which means that all of our usual notions of how to think about phases of matter constrained by the laws of equilibrium, thermodynamics should be revisited. What exactly is happening inside a time crystal? To understand this, we need to think about what a phase of matter really is. You know the three familiar phases: solid, liquid, gas. What distinguishes them is symmetry. A gas has no spatial order. Its molecules are equally likely to be anywhere. A liquid has short-range order. Nearby molecules are correlated, but distant ones are not. A solid, especially a crystal, has long-range order. The pattern of atoms repeats indefinitely across space. When water freezes into ice, it undergoes a phase transition. The continuous translational symmetry of the liquid, where any position is as good as any other, gives way to the discrete translational symmetry of the crystal, where atoms can only sit at specific positions in the lattice. The symmetry is broken. The water has chosen a particular arrangement, one among infinitely many possibilities. This is what physicists call spontaneous symmetry breaking, and it is one of the most important concepts in physics. The laws that govern a system can have a symmetry that the system's state does not share. The iron atoms in a magnet can all point in any direction. The laws do not care. But when the magnet cools, it chooses a direction. North becomes distinct from south. The rotational symmetry is broken. Spontaneous symmetry, breaking, is everywhere. It explains why magnets are magnetic. It explains why superconductors conduct without resistance. It explains, through the Higgs mechanism, why particles have mass. It is one of the deepest ideas in physics. And a time crystal breaks time translation symmetry in exactly this way. The drive has a certain period, call it T. The laws of the driven system repeat every time T, but the state of the time crystal repeats only every time 2T. The system has spontaneously chosen to oscillate at half the drive frequency. It has broken the discrete time translation symmetry of the drive. This is why time crystals are a genuine new phase of matter, not just an interesting dynamical phenomenon. They represent spontaneous symmetry breaking in the time dimension, something that was long thought to be impossible. But perhaps the most surprising discovery came in 2018, when physicists at Yale found time crystal signatures in a place no one expected. Sean Barrett, a professor of physics at Yale, had a graduate student named Jared Rovney who had grown some crystals for an unrelated experiment. The crystals were monoammonium phosphate, a compound commonly found in fertilizers and, as it happens, in crystal growing kits sold to children. Barrett had been following the time crystal research with interest. The experiments of Monroe and Lukin had used exotic quantum systems, trapped ions, and nitrogen vacancy centers that required specialized equipment and extreme conditions. Barrett wondered, could time crystal behavior show up in simpler systems? He and his students used nuclear magnetic resonance, the same technology that powers MRI machines in hospitals, to probe the monoammonium phosphate crystals. They applied periodic pulses to flip the nuclear spins and watched for the telltale signature of period doubling. Nuclear magnetic resonance works by placing a sample in a strong magnetic field, which aligns the nuclear spins. Then you zap the sample with radio frequency pulses, causing the spins to precess, to wobble around the magnetic field like tiny gyroscopes. By measuring the signals emitted as the spins relax back to equilibrium, you can learn about the local environment of each nucleus. Barrett's team used this technique to drive the nuclear spins in the monoammonium phosphate crystal with periodic pulses. If the system behaved like an ordinary material, the spins would oscillate at the same frequency as the drive. But if it behaved like a time crystal, the spins would oscillate at half the frequency. Our crystal measurements looked quite striking right off the bat, Barrett said. Our work suggests that the signature of a discrete time crystal could be found, in principle, by looking in a children's crystal growing kit. The implication was startling. Time crystals were not exotic, rare phenomena that could only be created in billion-dollar quantum computers or precision laser experiments. They might be everywhere. Every crystal that a child grows in a plastic container on the kitchen counter might contain, hidden within its atomic structure, the signature of this strange new phase of matter. To be clear, the Yale discovery raised as many questions as it answered. Finding the signature of a time crystal is not the same as proving you have a genuine many-body localized phase. The physics of why time crystal behavior would appear in ordered crystals without the disorder that theorists said was necessary remained unclear. But the discovery suggested something important. Time crystals might be far more common and far more accessible than anyone had imagined. As of the mid-2020s, time crystal research has exploded. Scientists have created time crystals in trapped ions, diamond defects, quantum computers, superconducting circuits, nuclear magnetic resonance experiments, Bose-Einstein condensates, and superfluid helium. Each platform has its own advantages and challenges. Each teaches us something new about this strange phase of matter. In October 2025, a team at Aalto University in Finland achieved another milestone. They created a continuous time crystal, one that oscillates spontaneously without periodic driving in superfluid helium cooled to near absolute zero. And for the first time, they coupled this time crystal to an external system, a mechanical wave on the surface of the superfluid, without destroying it. Perpetual motion is possible in the quantum realm, so long as it is not disturbed by external energy input, such as by observing it, explained Jere Mäkinen, the lead author. That is why a time crystal had never before been connected to any external system. But we did just that, and showed also for the first time that you can adjust the crystal's properties using this method. This development points toward practical applications. Time crystals might serve as exceptionally stable components for quantum technologies, memory elements that can preserve quantum information far longer than current alternatives. Today's quantum memories last milliseconds. Time crystals last minutes. That difference could be the key to building practical quantum computers. The most exciting thing, said Mäkinen, is that time crystals last for orders of magnitude, longer than the quantum systems currently used in quantum computing. The best case scenario is that time crystals could power the memory systems of quantum computers to significantly improve them. But let us step back from the practical applications and consider what time crystals mean for our understanding of nature. Physics, at its deepest level, is the study of symmetries and their breaking. The laws of nature are symmetric under translations in space and time. They are symmetric under rotations. They are symmetric under the exchange of particles and antiparticles. These symmetries are not decoration. They are the very foundation of the laws themselves. And yet, the world we live in is not symmetric. Matter exists rather than antimatter. Crystals have specific lattice structures rather than infinite translational symmetry. Magnets point in particular directions. The universe we observe is a universe of broken symmetries. For decades, physicists believed that one symmetry could not be broken in this spontaneous way: time translation symmetry. The flow of time, they thought, was inviolable. Systems could oscillate, sure, but only by drawing on external energy, only by depleting some reservoir. The ticking of a clock was always borrowed from somewhere. Time crystals show that this belief was wrong. Time translation symmetry can be broken, just like space translation symmetry. The flow of time is not so inviolable after all. matter can move in time without cost, just as atoms can be locked in space without effort. This does not mean we can build perpetual motion machines. It does not mean we can travel through time. It does not mean the laws of physics are wrong, but it does mean our intuitions about time were incomplete. It means the universe has more room for strangeness than we imagined. There is a story that physicists sometimes tell about scientific revolutions. The story goes like this. First, a new idea seems impossible, a violation of known principles. Then it seems possible but uninteresting, a technical curiosity. Then it seems interesting and inevitable, and everyone claims they believed it all along. Time crystals are somewhere in the middle of this arc. They no longer seem impossible. The experiments have settled that question. But we are still discovering whether they are merely interesting or truly profound. We do not yet know what role they will play in technology or in our theoretical understanding of nature. They might be a footnote in the history of physics, or they might be the door to an entirely new chapter. What we know for certain is this. There exists a form of matter that breaks time, not dramatically, not in a way that allows time travel or perpetual motion machines, but subtly, fundamentally, in a way that reveals that the flow of time is not so different from the extension of space. Crystals repeat in space. Time, crystals repeat in time. And the universe, it turns out, allows both. Frank Wilczek, the Nobel laureate, who started all of this in 2012, once reflected on what it was like to propose something so strange that many physicists initially dismissed it. Very few believed it at the time, and even fewer saw its importance, he admitted, echoing a comment that Philip Anderson made about his own localization theory decades earlier. Among those who failed to fully understand it at first was certainly its author. That humility is characteristic of the best physics. The universe does not care about our intuitions. It does not care what seems reasonable or what seems impossible. It simply is what it is, and our job is to listen. Time crystals are what the universe told us when we listened carefully enough. They are a reminder that even the most fundamental concepts, even time itself, can surprise us. They are proof that the quantum world, with its superpositions and entanglements and localizations, contains phases of matter we never dreamed of. And they are, in their own strange way, beautiful. Consider the atoms in a time crystal, flipping back and forth in their eternal rhythm. They are not alive. They have no purpose. They are just particles, obeying the laws of quantum mechanics. And yet, there is something almost organic about their behavior, something that seems to push against the entropic tide that pulls everything else towards stillness and disorder. The universe is dying, slowly, inevitably, as entropy increases and stars burn out and matter spreads thinner and colder through the expanding cosmos. This is the arrow of time, the direction of change, the reason we remember the past and not the future. But here, in a many-body localized system, time's arrow is blunted. Here, entropy does not increase. Here, motion does not decay. Here, in this small pocket of reality, time crystals tick on, undaunted by the march of thermodynamics. They are not immortal. Eventually, no isolation is perfect, and every time crystal will eventually couple to its environment and thermalize. But in principle, in the mathematics, in the ideal limit that physics allows us to imagine, they go on forever. A clock that never stops, a pattern that never fades, a structure in time as enduring as a diamond is in space. You began this journey staring at a clock. watching its pendulum swing, knowing that it must eventually stop. Everything stops. This is the wisdom of thermodynamics, the great leveler, the law that says all motion is borrowed and must someday be repaid. But now, you know something else. You know that the quantum world contains an exception, a loophole, a new kind of matter that dances to its own rhythm. You know that scientists have held this matter in their laboratories, have measured its oscillations, have confirmed that it is real. You know that time crystals exist. What you do with this knowledge is up to you. Perhaps you will become a physicist, drawn to the mysteries of many-body localization and non-equilibrium quantum systems. Perhaps you will simply carry this strange fact with you, a reminder that the universe is weirder and more wonderful than it appears. Either way, the next time you look at a clock, remember, somewhere, in a quantum computer or a diamond or a vat of superfluid helium, there is matter that does not obey the clock's tyranny. There is matter that has broken time itself, and it will keep moving, ticking, oscillating, long after everything else has stopped. But we are not quite finished. There is more to understand, more to explore. Let us go deeper into the physics, deeper into the questions that remain unanswered, deeper into what time crystals might tell us about the nature of reality itself. One of the most profound questions in physics is deceptively simple. Why does time flow in one direction? You can walk forward. You can also walk backward. Space does not care which way you go. But time is different. You can remember yesterday. You cannot remember tomorrow. Eggs break but do not unbreak. Coffee cools but does not spontaneously heat up. This asymmetry, the arrow of time, is one of the deepest puzzles in physics. The strange thing is that the fundamental laws of physics, the equations that govern particles and fields, are almost perfectly symmetric in time. If you watch a video of two particles colliding and bouncing apart, you cannot tell whether the video is playing forward or backward. The laws work equally well in both directions. And yet the macroscopic world, the world of eggs and coffee and human memory, has a definite direction. Time flows from past to future, never the reverse. The standard answer to this puzzle involves entropy. The universe began in a very low entropy state, the Big Bang, with matter and energy concentrated in a tiny, hot, dense point. Ever since, entropy has been increasing. Things have been spreading out, cooling down, becoming more disordered. The arrow of time in this view is just the direction of increasing entropy. But time crystals complicate this picture. In a many-body localized system, entropy does not increase. The system does not thermalize. It stays out of equilibrium indefinitely, not because energy is being pumped in from outside, but because the localization prevents the system from exploring its full configuration space. What does this mean for the arrow of time? Does time still have a direction inside a time crystal? In some sense, yes. The time crystal oscillates between states. There is a sequence, state A, then state B, then state A again, then state B again. This sequence is ordered. It defines a direction. But it is a loop, not an arrow. The crystal returns to its starting point over and over. It is not going anywhere. This is different from ordinary thermodynamic time, where systems move irreversibly toward equilibrium. In a time crystal, the motion is reversible. In principle, you could reverse the drive and make the crystal oscillate in the opposite phase. The direction is a choice, not a necessity. some physicists have speculated that time crystals might give us new insights into the arrow of time problem. If entropy can be held constant in a many-body localized system, if the usual thermodynamic reasoning does not apply, then perhaps we need to look elsewhere for the origin of time's direction. This remains speculative. Time crystals do not overturn the second law of thermodynamics. They simply exist in a regime where the second law is not the whole story. But they do suggest that the relationship between time, symmetry, and entropy is more subtle than we thought. Let us return to the experiments and examine them more closely. The details matter because they reveal just how difficult it is to create and study a time crystal. In the Monroe experiment at Maryland, 10 ytterbium ions were held in a linear Paul trap. A Paul trap uses oscillating electric fields to create a potential well that confines charged particles. It is named after Wolfgang Paul, who won the Nobel Prize in 1989 for developing the technique. Each ytterbium ion has a nucleus with a spin, and this nuclear spin can point up or down. In quantum mechanics, the spin does not have to be exactly up or exactly down. It can be in a superposition of both, a quantum state that has some probability of being measured as up and some probability of being measured as down. The experimenters used laser beams to manipulate these spins. One laser created an effective magnetic field that made the spins precess, like tiny gyroscopes. Another laser created interactions between the spins, making them influence each other. A third laser created disorder by giving each ion a slightly different local environment. Then came the periodic drive. The experimenters fired a sequence of laser pulses at the ions. The first pulse was designed to flip all the spins, to take every up spin to down and every down spin to up. But the flip was not perfect. It was deliberately miscalibrated so that the spins did not quite flip all the way. In an ordinary system, this imperfect driving would cause the oscillations to drift. If you flip the spins 97% instead of 100%, you would expect the system to gradually desynchronize, to lose its coherent oscillation. But that is not what happened. The spins oscillated at exactly half the drive frequency, period doubling, with extraordinary precision. Even though the drive was imperfect, the response was perfect. The time crystal was rigid. The researchers ran the experiment for 100 oscillation cycles, limited by decoherence, the gradual loss of quantum information to the environment. Over those 100 cycles, the period doubling remained stable. The time crystal held. Lukin's experiment at Harvard worked differently, but demonstrated the same physics. The nitrogen vacancy centers in diamond are atomic scale defects where a nitrogen atom replaces one of the carbon atoms in the diamond lattice, adjacent to an empty vacancy where another carbon atom should be. These defects have remarkable quantum properties. Their electronic spins can be controlled and measured with microwaves and lasers, and they maintain their quantum coherence for relatively long times, even at room temperature. The Harvard team used a chunk of diamond that contained about 1 million nitrogen vacancy centers. This was not a small, carefully prepared sample. It was a macroscopic piece of diamond, about the size of a grain of rice. The defects were randomly distributed throughout the diamond, providing natural disorder. The researchers used microwave pulses to flip the electron spins associated with each defect, and they measured the collective response of the system using optical techniques. What they saw was period doubling, the same signature Monroe's team had found with trapped ions. But there was something additional. The Harvard team observed not just period doubling, but also period tripling. In some parameter regimes, the spins oscillated at 1/3 the drive frequency instead of 1/2. This was significant because it showed that time crystals were not limited to period doubling. The symmetry breaking could take different forms. The system could choose to oscillate at any integer multiple of the drive period. The diamond experiment also highlighted the robustness of time crystal behavior. The nitrogen vacancy centers were embedded in an imperfect room temperature material, subject to all sorts of environmental noise, and yet the time crystal signature was clear. This suggested that discrete time crystals were not fragile, exotic phenomena, but robust phases of matter that could survive real-world conditions. The Google Sycamore experiment of 2021 took things further. A quantum computer is, in some sense, the ideal platform for time crystal research. Every aspect of the system can be controlled precisely. The qubits can be initialized, manipulated, and measured with extraordinary fidelity. The Sycamore processor used in the experiment contained 20 superconducting qubits. These are tiny circuits fabricated on a chip that can carry quantum information. Each qubit can be in a superposition of two states, and the qubits can be entangled with each other through controlled interactions. The researchers programmed the qubits to simulate a spin chain with disorder and periodic driving. They implemented the three essential ingredients of a discrete time crystal: interactions between the spins, disorder to induce many-body localization, and a periodic drive to break time translation symmetry. But the quantum computer offered capabilities that other platforms did not. In particular, it could run time backward. Not literally, of course. You cannot actually reverse the flow of time. But in quantum mechanics, unitary time evolution is reversible. If you know exactly what operations were performed on a quantum system, you can undo those operations and return the system to its initial state. The Sycamore experiment used this reversibility to probe the stability of the time crystal. They ran the drive forward for some number of cycles, then ran it backward for the same number of cycles. If the time crystal were perfectly stable, the system would return exactly to its initial state. Any deviation from perfect return would indicate decay or heating. What they found was remarkable. The time crystal was stable, within the precision of the measurement, correcting for known imperfections in the quantum computer. The time crystal did not decay. It maintained its coherent oscillation indefinitely. A key signature of an ideal time crystal is that it shows indefinite oscillations from all initial states, said Xiaomi, a Google researcher and co-lead author of the paper. The researchers devised a protocol to probe over 1 million different initial states in a single run of the machine, taking only milliseconds. This was like viewing a physical crystal from many angles to verify its repetitive structure. The verification worked. The time crystal passed every test. By 2024, time crystal research had expanded beyond the laboratory. Physicists at TU Dortmund in Germany created what they called a highly robust time crystal in a semiconductor material, indium gallium arsenide. Unlike previous time crystals, which required exotic conditions or sophisticated quantum control, this one formed almost naturally when the material was illuminated by continuous laser light. The crystal lived for millions of oscillation cycles, lasting about 40 seconds, a vast improvement over earlier experiments that ran for milliseconds or at most seconds. This longevity suggested that time crystals might eventually become practical components in quantum technologies. Meanwhile, theorists were exploring the boundaries of time crystal physics. In 2019, Valery Kozin and Alexander Kirienko of ITMO University in Russia published a paper showing that, in theory, a genuine time crystal, one without periodic driving, could exist in a system with long-range interactions. This was a different type of time crystal from the discrete time crystals that had been experimentally demonstrated, but it showed that Wilczek's original dream was not entirely dead, just more difficult to realize than he had imagined. The distinction between continuous and discrete time crystals became a subject of active research. In a discrete time crystal, the drive has a period t, and the crystal oscillates with period 2t or nt for some integer n. In a continuous time crystal, there is no external drive. The system spontaneously oscillates with some period that emerges from its internal dynamics. Continuous time crystals are closer to Wilczek's original vision, but they are harder to create and understand. The no-go theorem of Watanabe and Oshikawa applies to equilibrium systems, and continuous time crystals must find some way around it, typically by involving long-range interactions or open systems that exchange energy with their environment. In 2021, Andreas Hemmerich's group at the University of Hamburg created a dissipative time crystal using a Bose-Einstein condensate coupled to an optical cavity. In this system, atoms are cooled to near absolute zero, forming a quantum state in which they all occupy the same quantum wave function. The optical cavity is a pair of mirrors that bounces light back and forth, creating a standing wave that interacts with the atoms. Hemmerich's team showed that this coupled system could spontaneously break discrete time translation symmetry, periodically switching between two different atomic density patterns without any external periodic drive. The dissipation, the loss of energy to the environment, actually stabilized the time crystal rather than destroying it. This was a new paradigm. Time crystals protected by dissipation rather than localization. It opened yet another avenue for time crystal research. What can we do with time crystals? This question increasingly occupies physicists and engineers. The most obvious application is quantum memory. Quantum computers rely on qubits that can maintain their quantum states for long enough to perform computations. But qubits are fragile. They interact with their environment and lose their coherence, a process called decoherence. Current quantum memories last milliseconds at best. Time crystals, especially those based on many-body localization, offer a potential solution. In a many-body localized system, quantum information is protected from decoherence. The system cannot thermalize, which means it cannot lose its memory of its initial state. Time crystals last for orders of magnitude longer than current quantum systems, Markkinen noted. If time crystals could be integrated into quantum computers, they might serve as exceptionally stable memory elements. Another application is precision sensing. Time crystals oscillate with remarkable regularity, their period locked by the underlying physics rather than by any mechanical or electronic clock. This makes them potential candidates for frequency standards, devices that define a precise frequency reference. Frequency combs, tools that produce a spectrum of precisely spaced frequency lines, are essential for precision spectroscopy, optical clocks, and other measurement technologies. Time crystals might provide a new way to generate such combs, using their intrinsic periodicity rather than traditional laser-based methods. And then there is basic research. Time crystals provide a new window into non-equilibrium quantum physics, a domain that is poorly understood compared to equilibrium physics. By studying time crystals, physicists learn about many-body localization, thermalization, and the boundaries of statistical mechanics. We think that the most exciting use for quantum computers right now is as platforms for fundamental quantum physics, said Matteo Ippoliti of Stanford, co-lead author of the Google Time Crystal paper. With the unique capabilities of these systems, there is hope that you might discover some new phenomenon that you had not predicted. Let us pause and consider what we have learned. In 2012, a Nobel laureate proposed that matter could break time symmetry, oscillating forever in its lowest energy state. Physicists proved this was impossible in equilibrium. But then they found a loophole. Periodically driven systems with many body localization could break discrete time symmetry, oscillating at a fraction of the drive frequency indefinitely without absorbing energy. In 2017, 2 experimental groups built the first discrete time crystals using trapped ions and diamond defects. The time crystals were real. In 2018, physicists found time crystal signatures in ordinary crystals, the kind you can grow at home. In 2021, researchers used a quantum computer to create and verify a time crystal with unprecedented precision. They showed it was stable in principle, not just in practice. In the years since, time crystals have been observed in semiconductors, superfluids, superconducting circuits, and many other systems. They have become a recognized phase of matter, studied by hundreds of research groups around the world. And they have changed our understanding of time. What does it mean to break time? This question sounds almost metaphysical, the kind of thing a philosopher might ponder rather than a physicist. But time crystals give it concrete, measurable meaning. In our everyday experience, time is a river that flows in one direction. We are carried along by it, helplessly, from past to future. We can move freely in space, going left or right, or up or down, but we cannot move freely in time. We are trapped in the present moment, watching the past recede and the future approach. Physics has long suggested that this everyday experience might be misleading. Einstein's theory of relativity treats time as a dimension, much like space. A 4-dimensional space-time with 3 dimensions of space and 1 of time provides the arena in which all events occur. From this perspective, the flow of time is an illusion, a consequence of our limited perception, rather than a fundamental feature of reality. But even in relativity, time and space are not quite equivalent. Time has a different mathematical sign in the space-time metric, a technical detail that distinguishes it from the spatial dimensions. And in our experience, time still feels fundamentally different from space. We remember the past, but not the future. Causes precede effects. Entropy increases. Time crystals add a new piece to this puzzle. They show that matter can be periodic in time, just as it can be periodic in space. They show that the symmetry of time translation, like the symmetry of space translation, can be spontaneously broken. In this sense, time crystals make time more like space, revealing a deeper symmetry between the two. Some physicists have speculated that time crystals might have cosmological implications. The early universe underwent a series of phase transitions as it cooled, breaking symmetries and giving rise to the particles and forces we observe today. Could time translation symmetry have been broken in the early universe? Could there be cosmic time crystals, oscillating structures on astronomical scales? This is speculation far beyond what current experiments can test, but it illustrates how time crystals stretch our imagination, forcing us to reconsider assumptions we did not even know we were making. Time, we used to think, was inviolable. Energy is conserved because the laws of physics do not change with time. Motion must decay because entropy must increase. Perpetual motion is impossible because you cannot cheat thermodynamics. Time crystals do not overturn any of these principles. Energy is still conserved. The time crystal's oscillation does not create or destroy energy. Entropy does not decrease. It merely stays constant in the many-body localized phase. Perpetual motion, in the sense of machines that produce useful work from nothing, remains impossible. You cannot extract energy from a time crystal without putting energy in first. But time crystals reveal that the relationship between time and matter is more subtle than we thought. They show that motion can persist without decay, that order can exist in time as well as space, that the flow of time can be broken into a repeating pattern as surely as the extension of space can be broken into a crystal lattice. This is not a practical revolution. We will not power our cities with time crystals or travel to the past. But it is a conceptual revolution, a shift in how we think about one of the most fundamental aspects of reality. Time, it turns out, is a dimension like space. And just as matter can break the translational symmetry of space, forming the crystals that glitter in our jewelry and structure our semiconductors, matter can break the translational symmetry of time, forming structures that tick and oscillate in an eternal rhythm. The universe allows this, and that is worth knowing. There is one more thing to consider, and it is perhaps the strangest thing of all. Time crystals are quantum phenomena. They depend on quantum mechanics, the superposition of states, the entanglement of particles, the discrete energy levels that prevent thermalization. Classical physics does not allow time crystals. Only quantum physics does. This raises a question. Does classical physics even make sense at the quantum level? Is there a smooth transition from the quantum world of time crystals to the classical world of everyday experience? This is the measurement problem, one of the deepest puzzles in quantum mechanics. Quantum systems exist in superpositions of states until they are measured, at which point they collapse into definite outcomes. But what counts as a measurement? How does the weirdness of quantum mechanics give rise to the definiteness of classical physics? Time crystals do not solve the measurement problem, but they do illustrate something important. They show that quantum mechanics allows phases of matter that have no classical analog. They show that the quantum world is richer and stranger than we might have guessed, containing phenomena that exist only because of quantum effects, phenomena that classical intuition could never have predicted. As we probe deeper into the quantum realm, we should expect more surprises. Time crystals are just the beginning. You began this journey watching a pendulum swing, knowing it would stop. Now you know that in the quantum world, there are systems that do not stop, that oscillate forever, that break time itself. This is not science fiction. This is not speculation. This is experimental physics, confirmed by multiple independent groups using different techniques in different materials. Time crystals are real, and they invite you to reconsider your intuitions about time, about motion, about the deepest laws of nature. The next time you look at a clock, consider this. The ticking you see is borrowed motion, energy draining from a spring or battery, entropy increasing with every swing. The clock is dying, slowly, as all clocks must die. But somewhere in a physics laboratory, somewhere in a quantum computer, or a diamond lattice, or a superfluid cooled to a millionth of a degree above absolute zero, there is a different kind of ticking. A ticking that does not drain any spring. A ticking that does not increase any entropy. A ticking that, in principle, could continue forever. This is time crystallized. This is motion without decay. This is the universe revealing, once again, that its mysteries are deeper than our understanding, and that the strangest things are often true. Time crystals exist. They break the laws of physics only in our imagination, not in the mathematics of quantum mechanics. They are real, and they are waiting to teach us more about the nature of time, the nature of matter, and the nature of reality itself. The pendulum swings, the clock ticks. But in the quantum world, something else is happening, something that never stops. This is the new physics of time, and we are only beginning to understand it. Perhaps one day, the technology born from time crystal research will transform our world, enabling quantum computers that can solve problems beyond the reach of any classical machine. Sensors that can detect signals too faint for any other technology. Clocks that keep time more precisely than anything we have imagined. Or perhaps time crystals will remain a curiosity, a beautiful example of what quantum physics allows that classical physics forbids. Either way, they have already changed how we think about time, and that change is permanent. The universe has spoken. It has told us that time, like space, can be crystallized. It has shown us that the quantum world contains wonders and mysteries we never dreamed of, and we will never see time or space or the strange dance of atoms and electrons quite the same way again.